I have a stupid question for you. Which of these two objects weighs more? The big fluffy cloud in the upper left corner or this cast iron anvil in the lower right? You see, I told you that was a dumb question because hopefully you're thinking, well, doesn't that depend on how big the cloud is? If you were to just grab a chunk of that cloud with your hand, one fistful, it wouldn't weigh very much at all. But if that cloud is the size of a skyscraper or a small mountain, even though it's made out of fluffy, gaseous water, it probably weighs quite a bit more than the anvil over here. So you could clarify things by imagining a cloud that's the same size. This has got to be just between 1 and 2 feet across. It's kind of silly, but imagine a cloud that's just 2 feet across. Now it's clear that the anvil weighs more. So for equal volumes, let me grab the laser pointer. For equal volumes, clearly the anvil would weigh more. Now, if we were to scale up the size of the cloud, if we made this cloud twice as big in diameter or length, whatever the parameter is, I think it would be fair to say that the cloud would have twice as much mass, twice as much stuff, so it would weigh twice as much. And mathematically, we would say that, or that's equivalent to saying that the mass is proportional to the volume. Same thing goes for the anvil. If you could double the volume of this anvil, but have it made out of the same material, you would expect it to weigh as much because it would have twice the mass. So that's what the statement says. Tripling the volume would consequently triple the mass. So going back to the scenario where these two have equal volumes, can you put into words why, despite having the same diameter, let's say, the anvil weighs quite a bit more? It's because the anvil's got way more mass packed into that same volume. And there's a word for that. Something that's got more mass packed per volume, we say that it's more dense. So we use this Greek letter down here, rho. This is the Greek letter rho. It looks like the letter P. And I think we can also conclude that mass is proportional to density. So if these, again, were equal volumes, it's kind of silly to imagine a cloud that small, but if the cloud was the same size, diameter, as the anvil, then if the anvil were 3 times as dense, that would mean that the anvil had 3 times as much mass. So we can simultaneously make these two statements of proportionality. For an object of given density, like the cloud, if you're talking about a cloud that's got twice the volume as another cloud, it should also have twice the mass, assuming that they're made out of the same composition. And for 2 objects of equal volume, the one that's more dense would, of course, have more mass or be more massive. So something that's triply dense compared to some other object would be triply massive. What else can we say about this? Yeah, let's combine those two statements of proportionality. And this is something that we'll do repeatedly throughout the semester. If mass is proportional to both of those, then we can actually say that mass would be proportional to the product of these two. So let's look at this statement here. What would you expect to happen to the mass of an object if you doubled its volume and tripled its density? Well, doubling the volume for fixed density would mean twice the mass as well. But then if you then triple the density, you should expect the mass to go up by another factor of 3. So overall, you would have 6 times the mass. And that's why we write it as the product. If this goes up by a factor of 2 and this goes up by a factor of 3, then the whole thing, mass, would go up by a factor of 6. And we don't actually need this constant of proportionality. We can replace it with an equal sign. And now what we've actually done is to define density, or the units of density, in terms of the units of mass and the units of volume. So let's solve this equation right here, which you should probably memorize. Let's solve that for rho, the density, and we get this formula. And many of you probably knew this already. And just looking at this formula, we see that it makes sense, because just a moment ago I was saying that if you pack more mass into a smaller volume, you're talking about a greater density. And we know that if we make the numerator bigger, that tends to make the density go up. And if we make the denominator smaller, that would also tend to make the density go up. So the more mass you have concentrated in a given volume, the greater the density. And the units here, since chapter 1 talks a lot about the SI units, standard units that are used in physics. We measure mass in kilograms. That's a little tricky because kilo is that prefix that means 1,000, and you might be inclined to think that the standard unit shouldn't have any prefix associated with it. But it turns out that a gram's not really convenient for a lot of purposes. Like if you're talking about the mass of the sun, that's a really big number, whether you use grams or kilograms, but it's even bigger if you use grams. So kilogram is more convenient for a lot of everyday applications, like if you're talking about the mass of water, which is what we'll be doing in this lab. And then down here, volume will go with meters times meters times meters, or cubic meters, not liters. A liter, if you're curious, is 1,000th of a cubic meter. A cubic meter is pretty large volume, is it not? Because a meter is more than 3 feet. So imagine a big box that's more than 3 feet on a side. That's a large box. When it comes to exotic things like planets, astronomers are now discovering all kinds of planets far away, orbiting other stars. And one of the most common types of planets that they're discovering is called the hot Jupiter. So of course it's not really Jupiter, because Jupiter is in our solar system, but those are planets like Jupiter. But because they're close to their host stars, they're extremely hot and they tend to puff up. And as a result, they have very low density. So the density of this puffed up planet could be much lower actually than the density of water, believe it or not. And contrast that with what they often call terrestrial planets, meaning planets like Earth that are composed of rock and metal. And those can easily be 5 times as dense or more compared to these hot, puffed up Jupiter-like planets. Of course, we live on one of those terrestrial planets. Now, you should keep in mind that this formula really describes the average density of something. Now, when I was looking at the cast iron anvil, presumably the composition of that anvil was uniform throughout. It's not like it was one type of metal in the top half and another type of metal in the bottom half. I'm assuming it was the same throughout. If that's the case, then it's got one value for density. You just take the total mass and divide by the total volume. But the Earth, of course, has different densities depending on where you're looking. The core would be the most dense. The oceans are significantly less dense than the core. So you can take a look at these numbers here. So just be aware that this density here would really be a function of position within the Earth. Rho is going to take on different values depending on where you are. If you were to take the entire mass of the Earth and divide it by the total volume, that would give you a number called the average density. And the average density is going to be somewhere between the very high density of the core and the much lower density of the crust. In this lab, you will be measuring the density of water, and I just realized I meant to show you a table of common densities in that PowerPoint, so I'll go back and do that in a moment. But you'll be measuring the density of water and hopefully ice as well if you choose to do that. And you're going to, in order to do that, you'll have to pour the water into some sort of form that has a particular volume. I'm going to look at the case of a cylinder because I suspect many of you will go with the option that I chose, which is a cylindrical form of cardboard, or made of cardboard. I chose to use a rolled oats container. Not Quaker Oats, I went with the generic store brand, but it's got a circular base, vertical walls. So what is that, a right circular cylinder? And there's a simple formula for the volume, of course. If I call this the radius capital R, and here's the height, which I'll call H. And then the area of the base, we all know, I hope we all know, is pi times R squared. A lot of people surprisingly don't know that coming into this class. It's easy to remember that it's pi R squared because since you're talking about area, the units would be square meters, right? Not just meters. So it can't be 2 pi R because that doesn't have meters squared in it. All right, and a lot of you know that the volume in cubic meters of this right circular cylinder would be the area of the base times the height. In other words, pi R squared times the height. Now, measuring the radius directly is not always convenient. Wouldn't it be easier just to lay a ruler across the top of this thing and measure the diameter? That's going to be easier than putting like the left end of the ruler at what you think is the center of the circle and then measuring over to one edge. Now the diameter, or I should say the radius here, is 1/2 of the diameter. Now when you plug in a 1/2 diameter and square it, you're going to pick up a 1/4 because you're squaring the 1/2. So the volume could also be written, I'm going to put the 1/4 out front. That's 1/4 pi d squared h. There it is. There's the formula for the volume of a right circular cylinder in terms of its diameter, capital D, and its height. And you can do that in whichever units you prefer. If you're using a ruler, probably the easiest thing would be centimeters. Now you just saw that the density of an object with uniformly distributed mass, I should just say uniform density, something that's made out of the same material throughout, is just the total mass over the total volume. So this is going to go into the denominator. Now, what happens if we divide by 1/4? Wouldn't that be the same as multiplying by 4? So that 4 would come up top. And we would wind up with density being 4m over pi d squared h. Great. So you only have to make 3 measurements of your right circular cylinder filled with water in order to determine the density. You're going to have to measure the mass, the diameter, and the height. Now these 2 measurements can be done with a ruler, which I'm assuming you have. The only one that may give you some trouble is the mass. You could throw this onto a bathroom scale, but it's probably not going to give you a very accurate reading or a very precise reading, because I'm assuming that your right circular cylinder is nowhere near as heavy as a person's body. And bathroom scales tend to give your weight to the nearest 1 pound, let's say. We're going to need something with more precision than that. So I'm going to use a kitchen scale. But each of these 3 measurements will have their own absolute uncertainties, which will propagate into an uncertainty in the density. So the idea is to come up with the best value for the density of the water and then state a range of probable values. You know, it'll be rho best plus or minus delta rho, where delta is the absolute uncertainty. We need to find the best value plus or minus delta rho. Well, the best value is easy. You just plug in your measurements of these 3 quantities and call that rho best. But determining this is going to require use of that formula that was covered in the previous video, the error propagation video. So I'm going to help you out big time here and just big time and write the formula that you've already looked at, but this time I'll use the appropriate variable. So remember, if you're multiplying and dividing, if that's the function that you're dealing with, then you can relate the relative uncertainty in rho to the relative uncertainties in these measurements. And this is how it goes. The relative uncertainty in the density, we're going to have a term for relative uncertainty in the mass, relative uncertainty in the diameter, relative uncertainty in the height. And each of these terms must be weighted by their exponents. So when we look at the formula, mass and height are both being raised to the first power. It's only the diameter that requires a factor of 2 out front. And the first formula I presented would have just been this. But remember, this formula is a little pessimistic. A more reasonable estimate of the propagated uncertainty would be to add these in quadrature. So put parentheses around these, square them, add them all up, and then don't forget to take the square root, of course. This is the formula that you will implement if the form that you choose is a right circular cylinder. Some of you, I don't know, maybe you've got an old fish tank at home, which is a nice rectangular shape, and you know that's big enough to put enough water in there that you could actually use a bathroom scale because it would be more heavy. Of course, then you're going to have to lift it. I wouldn't want to do that. But maybe you've got some kind of transparent plastic rectangular tank, box, whatever, and that would be easier for you. You're welcome to do that. I'll show you what I did with the rolled oats canister. What else can I say about this? Once you've determined the relative uncertainty, we'd like to convert that back into an absolute uncertainty. So delta L, delta rho would be the relative uncertainty times your best estimate. So you've already plugged in your measurements. You've determined the best value for rho. Take that best value and multiply it by your relative uncertainty. Like if this all comes out to be 0.04, for instance, 0.04, well, that's 4%. So you would take 4% of your best estimate, and that would be your delta rho. I'm not going to discuss here the rest of the steps, how you would turn that into a statement about the lowest probable value and the highest probable value. That was already covered in the error propagation video. So refer to that video for exactly how to proceed and state your final result. And now I think we'll go to the kitchen and take a look at how this is done. I almost forgot I was supposed to take a quick look at a table of common densities. Look at the range here. Gold is as high as almost 20, and hydrogen gas is many orders of magnitude lower than that. You may notice the one that really pops out, the easiest of all, is the density of water. It can't be a coincidence that water has such a nice, easy number as its density. And laser pointer is my friend. Grams per milliliter. That's not an SI unit of density. The SI unit would be kilograms per cubic meter, but this is actually a very convenient unit of density, and it's the one that you'll probably want to use for this lab, because I'm going to measure mass in grams with my kitchen scale, and a milliliter is actually the same as a cubic centimeter. Centimeter times centimeter times centimeter. So if you measure all your distances in centimeters, your volume will come out in cubic centimeters, which is the same as milliliters. Okay, so right, it's no coincidence that a cubic centimeter, which is a milliliter, or that the density of water is 1 gram per cubic milliliter, because the liter was actually defined originally in terms of water. That's why it comes out so nice. Okay, some numbers that I have memorized. I've done aluminum in this lab a number of times. We're not doing that because we don't have the classroom, but 2.7. So densities like 2, 3, those are the lightweight metals. It's kind of surprising how dense copper is. Gold is extraordinarily dense. We normally think of iron as something that's really heavy. When I showed you that picture of the anvil, I'm sure you sensed that that thing was really heavy, but it's not even that dense compared to some of the other metals. Look how much more dense lead is. If you go to the gym, I believe those weights are iron. They might be an alloy, but they're not lead. And they're certainly not gold. Well, not even at Gold's gym. But mercury, that's shocking just how dense mercury is. That's almost twice the density of iron. Can you imagine lifting a vial of mercury? Or if you took a 1 liter, think about it, if you took a 1 liter water bottle, just dumped out all the water and filled it up with mercury, look at the comparison of the densities here. That one bottle of mercury would weigh as much as almost 14 bottles of water. That's hard to imagine because I've never actually picked up that much mercury. Sand, around 2. So if you're thinking of planet Earth, there's a whole lot of silicon in planet Earth, which I think is the main element in sand. So that's probably similar to the density of much of the Earth, not the core, of course, because that's made out of metals. In any case, you're just trying to confirm this number. That's what this lab is about. Normally, we would measure a little chunk of copper and a chunk of aluminum and confirm those numbers. But since we don't have that luxury, we'll go with water, because everybody's got that. I sure hope so, since we're in a first world country here. Okay, you see here I have my kitchen scale. I forget what I paid for this. It wasn't much. I'm hoping that since you're in groups of 3, at least one person in your group either has a scale like this already or has a friend or family member that does. So if you don't have one, please ask around. You've got 2 weeks to do the lab. You could even ask somebody else in the class if they've got one that you can use. Or you could do this. You could go down to the local supermarket, go to the meat department and say, hey, I'm doing this project for my physics mechanics class. Would you mind would you mind doing this for me? Can you fill this with water and determine the mass? Because they've got that fairly precise scale on the meat counter there. So this is what I'm going to use, because I found, I'll show you what I tried to use originally. I thought I would have some success with the glass like this, because it looks like the walls are vertical, but the value I got for water's density was terrible. And I realized it's because the walls are actually tapered. Maybe you can see my finger rising. You can't see that, but
take my word for it. It's difficult to tell, but the walls are not actually vertical. So you may have similar difficulty if you try to use the drinking glass. This was perfect. This was a $1.50 from Albertsons, wherever I got it from. I think it was Winco. And hey, you get your insoluble fiber while you're at it, and a piece of physics lab equipment. You don't have to use this. If you've got something else that would work, go for it. Be creative, but this was a good solution for me. I need to make those 3 measurements: mass, diameter, and the height. And while I'm at it, I will estimate the absolute uncertainties. So perhaps the first thing I should do is to figure out what is the absolute uncertainty in this scale here. So let me go grab some quarters because I have an idea for how to do that. I just Googled the mass of a US mint $quarter and found from Google that it was 5.670 grams. Well, rather than measure the mass of 1/4 by itself to see how accurate the scale is, I've got 6 quarters here. Is it 6? No, I can't even count. 8 quarters. I've got $2 worth of quarters here, and I'll set them on the scale. The scale is telling me that these 8 quarters have a mass of around 46 grams. You saw it fluctuate a bit there. So I'm going to take 46 grams and divide it by 8 quarters to see what the mass is per quarter. 5.75. Well, if the actual value of the mass of a quarter really is 5.67, it looks to me like I'm off by less than 1/10, right? Because 5.67 plus 1/10 or 0.1 would be 5.77, which is even higher than this. So you could make the case that this thing is as precise as, or it's accurate to the nearest 1/10 of a gram, but I'm going to be even more liberal than that, because you notice that the last digit there fluctuated. In fact, now it's saying 45. I think it said 46 just a moment ago. And if I change the way the mass is distributed, I feel like I'm playing a card game here. Okay, now it says 45. I know it said 46 earlier. So I think that last digit could easily be uncertain. So after I measure the mass of this water, I'm just going to add a plus or minus 1 gram. That will be my chosen absolute uncertainty. Of course, if we were using one of the chemistry scales or one of the triple beam balances that we have on campus, we could do much better than that, but we'll deal with what we have. Okay, so give me a moment. I'm going to fill this up with water. And actually, I almost forgot. I want to tare or zero it. So this cardboard itself, or whatever this is, the canister has a mass of 54 grams. I want to subtract that out from the total mass. So if I hit tare, it'll go back to 0. And now when I fill it up with water, it will only give me the mass of the water. It will have subtracted the mass of the paper itself. I tried my best to get the water up to the very top without spilling. Give you a little peek there. Can you even tell that it's full? All right. And that number does not look familiar. I just did this the other day and I saw a very different number. So that's a little concerning, or maybe I've just forgotten. So I'm going to write that number down and hope that it's correct. 1,243. Oh, no, it's 1244. I'll go with 1243.5 plus or minus 1 grams. I'm measuring mass in grams. And now I can dump this water out and measure the diameter across the top here, and of course the height. And I'll point out, I was hoping to also use this thing to measure the density of ice. So what I did was fill this with water, put it in a bowl, and then leave it in the freezer overnight. But after a few hours, the water caused the bottom to dissolve and it just spilled out. So that didn't work, but I happen to have this right here. I think this would work really well. So something else I'm going to try, and I hope that some of you do this as well, would be to fill this with water, leave it in the freezer overnight, and then the next day, just cut off the plastic and you'll have a nice brick of ice in this particular shape. I'm pretty sure we can use calculus to come up with a formula for this shape in terms of the top diameter, the bottom diameter, and the height. So I'll be taking a look at that. I could cheat and look that formula up online, but it would be cooler to use the integral calculus to do that ourselves. Okay, I've dumped out the water, and now I'm going to measure the diameter across the top here using centimeters. I'll try to hold this up to the camera. This is going to be a learning process for me, not being a total klutz when it comes to this sort of thing. So I'm sure you don't have a real clear view here, but I'm coming up with a number close to 9.5. It's very close to 9.5 centimeters. Now, if you were to look real carefully, you might decide that you could measure the diameter to the nearest millimeter, not just the nearest centimeter, but the nearest tenth of a centimeter or millimeter, because the meter is graduated into millimeters. However, think about it. This thing's not perfectly round, is it? Even when I'm not squeezing it, it's probably not perfectly round. And where exactly the water would go from the inside to the inside. Maybe you'd have to take into account the thickness of the paper as part of your uncertainty. So I think that saying that the uncertainty is a tenth of a centimeter or 1 millimeter would be too optimistic. I'm going to go with 9.5 plus or minus, and then I have to decide. And you know what? In the previous video on error propagation, I was a little cavalier when it came to estimating absolute uncertainties. At one point, I said that half a centimeter might as well be the same as 0.2 centimeters. That's probably a little sloppy. I should have said 0.5 centimeters versus 0.4 centimeters is a bit of a toss-up. But I do want to put some effort here into making a good estimate of my absolute uncertainties. So if I'm looking at the ruler here, I can definitely do better than the nearest centimeter. I'm going to go with maybe 3 millimeters or even 2 millimeters. Let's say 3. So 3 millimeters would be 3/10 of a centimeter. Sorry about the camera angle here. So 0.3. Even that might be overestimating, too pessimistic. Centimeters. Yeah, I think I'll probably change that back to 0.2 later. Now for the height, this is definitely an uncertain measurement because we have to take into account the fact that there's this lip here. I could try to, let's see here. Yeah, I can just tell by looking, that's a full centimeter. But doesn't this thing sag when it's filled with water? It probably does sag. So it's difficult to tell exactly how high the column of water is when this is full. So what I'll do is I'll measure from the bottom of the paper here to the top, and then I'll subtract a little for that lip. I'll subtract about 1 centimeter, and then maybe I'll add a little bit back in to account for the fact that the paper sags. So I'm finding that the height here is 18 centimeters, which is probably not coincidental. They probably picked that on purpose when they designed it. So 18 minus the lip would be 17, but there's that sag. So I'm going to go with 17.5 centimeters for my height. Plus or minus, and then there's definitely some uncertainty there. It could be as high as almost 18 because of the sag. How about we go with just 0.5 centimeter as the uncertainty? I think those numbers are good. Like I said, I'll probably change that one back down to 0.2. So what I'll do now is put these numbers into a spreadsheet. I'm going to use Excel to help me implement the formula that we were just talking about in order to carry out the error propagation rather than do everything by hand or using a hand calculator, pocket calculator. We'll go with Excel.
So here's my template spreadsheet. I'm going to put basically this spreadsheet on Canvas. It'll be posted with the assignment description. And that means some of the typesetting's done for you. You probably want to change this to something like water sample. That's real creative. Now, what's not going to be done for you is the formulas. It's up to you to enter the formulas. You'll see what I'm talking about in a moment here, but let me type in my mass in grams. 1243.5 was the value that I came up with. And my diameter, I guess I'll change this to capital D just to be consistent with what you saw a moment ago. And I'm going to be compulsive and make sure it's bold type like everything else. Okay, the diameter I thought was 9.5 centimeters and the height was 17.5. All right, and down here is where I'm going to enter my absolute uncertainties. See, it's very clear. I've used the the delta letter. I've got my units. Anytime you present numbers in a table like this, you definitely want to emphasize what your units are. It doesn't have to be the units that I'm using, as long as I know what your units are. But if you were to do things in meters, you'd have numbers here like 0.17 instead of 17, which is what it would be for centimeters. So I think these are the most convenient units. I estimated the uncertainty of the mass to be something like 1 gram for the diameter. Remember, I wrote down 0.3, but then I amended that to 0.2. I think I was being a little too pessimistic. For the height, I went with 17.5. Oh, I'm sorry, that was the value of the height. The uncertainty was definitely half a centimeter because of that, the bottom that could be sagging under the weight of the water. Now here, I thought I had already done this, but a word of advice. It's a little annoying at first to figure out how to write the syntax for the formula. Entering formulas into Excel can be a little tedious, but the payoff is once you've entered the formula, if that formula refers to other cells, then if you go change some of your input values, your output will automatically update and you don't have to recalculate it. So it's really worth the effort it takes to put the formula in. And I guess I'll go ahead and show you just this part. I hid the formula bar so you wouldn't see what I was entering, but I'll go ahead and make that visible again. You'll have to enter this part by yourself. Downstairs, or downstairs in the spreadsheet, there's the section for error analysis. I'll leave it up to you to enter those formulas. But here I'm going to say equals. You've got to use the equal sign anytime you're going to do math in Excel. And remember that formula was 4 times the mass over pi d squared h. So 4 asterisk, so shift 8, 4 times the mass. Now here's where instead of typing m, I'm going to click on the cell that contains the mass. Click on the cell and see how the computer's identifying that as cell A4. And then I will divide by, now I could wrap the entire denominator in parentheses, the way you would normally do in algebra. But what I'm going to do instead, take a look at that formula. If you're dividing by the quantity pi d squared h, you can actually divide by pi, then divide by d squared, then divide by h. And I do that because I would prefer to have multiple division signs over nested parentheses. The nested parentheses are no fun. So first I need to divide by pi. And in Excel, you do that like this. You type the word pi and then just put empty parentheses. And the computer will know that's 3.14159 and a bunch of digits after that. And then I will divide by the square of the diameter. So I click on the cell for diameter and the caret symbol, that's shift 6. That means raise that number to the second power. I'll type 2. And then after that, I want to divide by the height. So that's it. That's the whole formula. So again, what I was saying is starting from pi onward, you could have enclosed that whole thing and put multiplication symbols in there instead of division. That's just a little algebra there that I know some of you have forgotten. So if you're confused, I don't know, you could ask me, or you could get out an algebra book, ask your math teacher, or don't ask anybody because you're embarrassed. I'm going to hit enter. Ooh, I got lucky. Check that out. I was hoping for a density of 1.00, and it came out very close to that. And of course, is the density of freshwater 1.0000 anyway? You know, at the time, the density, or at the time the milliliter was defined, they didn't have super precise measuring instruments. So if we used modern standards and measured the density of fresh water with extremely precise devices, we might actually find that it's 1.0007. That's a number you could look up on Wikipedia, but also keep in mind, when things get warmer, they tend to expand. So the density of water would actually depend on the temperature and even the atmospheric pressure on that given day. So there's a range of values for the density of water. I'm just happy that it came out pretty close to the desired value. So down here, delta rho over rho, you're going to have to enter a formula here, and I'm not going to click on it. Let me go ahead and hide formula bar again. It's up to you to enter a formula in this cell. You're going to hit equals, and then you just have to take the uncertainty in rho and then divide it by your best value for rho. Now, where do we get the uncertainty for rho? I think that would be this cell. No, I'm sorry. Remember the formula that I talked about? You get this in terms of the other uncertainties. So this is where you enter that gnarly formula with the square root and the other terms squared, you know, added in quadrature. It's up to you to enter that. and I will be checking to see if yours works. So you're going to have different values here, of course, because you won't be using my rolled oats canister, but I'm still going to have my spreadsheet up, and I will check that the propagated uncertainty that I get is consistent with yours. And if you ended up using a different shape, I guess I'll have to do a little bit more work to check that, but make sure you enter those formulas correctly. And notice I've written percent here. So after using the formula, I would have multiplied by 100 to convert that into an uncertainty, or into a percent uncertainty. Without the multiplication by 100, this would just say 0.051, but it's easier to think of it as 5%. Okay, and you'll convert that back into an absolute uncertainty. You can review how that's done. I think I talked about it in this video, but I also went over it in the error propagation video. And then lastly, you might as well state it as a range here. So there's no formula here. That's just text, less than rho, less than. Here is where I said, okay, equals, and you take your best value for rho and subtract the uncertainty. And then here you take your best value for rho and you add your uncertainty. So I think it's kind of surprising that the number I got was so close to the expected value. The last thing I'll be looking for, it sounds like I'm being facetious here, but not really, is, it's supposed to say something smart, not same. All right, I'll fix that. But you need to say something intelligent about how well your result agrees with the accepted value of the density of water. So let's say your number doesn't come out to be 1. Let's say it comes out to be 1.1, which is not correct. When you do the error propagation, you're going to find a range of likely values around 1.1. And as long as the true value or the accepted value of water's density, freshwater density, falls within your range, you can conclude that you made your measurement correctly. So let me see if I can just fudge one of the numbers here. This is just fictional to demonstrate what I'm talking about. Yeah, check this out. Let me go with something more ridiculous. Yeah, okay. If I had found that my best estimate for the density was 1.46, that's much higher than 1, and here's my range, even my lowest likely value for the water that I was measuring is significantly higher than the accepted value. So I would be forced to make a conclusion here. Either I screwed up, maybe I didn't use the formula correctly for calculating density, maybe I entered one of my measurements wrong, or maybe I grossly underestimated. I did a poor job of estimating my absolute uncertainties. That's also a possibility. Or I could say, hey, I did everything right. I was very careful. I revisited my measurements multiple times. I didn't screw up. So evidently this liquid that I measured ain't water. It must be heavy water. I must somehow have my hands on purified heavy water where every atom of, what would that be? Every atom of hydrogen has 2 neutrons next to it. I think that's called deuterium, or is it tritium? I forget. So that's one conclusion you could draw, but that would be a little silly. So just figure out the most likely explanation. What is the point of all this? Well, it's a lot more satisfying when you can state a range of likely values for the thing that you were measuring. You can draw more meaningful conclusions. And it also it helps you figure out where you went wrong. Okay, so we will be repeating this process for at least 2 more labs this semester. And there's not a lot here, right? I'm not asking for an introduction, an abstract, procedure. I just want you to present your data, use the formulas correctly, and say something intelligent here at the bottom. So I'm looking for a couple sentences, and I will present all of these requirements in a short list and include it with the assignment description. So if you have questions, ask your friend. All right, where's the pause button? Here it is. Yes, the last thing I meant to say. I'm only going to require that you do this for 1 sample, but I'm hoping some people choose to do ice. So you can skip the liquid water, go straight to the ice, and that means you're probably going to have a shape that's a little more tricky. You might have to look up a formula for the volume. If you want to do both, maybe I can throw just a couple extra points your way. Each of these labs will be worth 20 points. So maybe 2 extra points for doing 2 samples, as long as you do it correctly.